Good evening, everybody. Patty, you are more than 200 attendees now, so it's a lot. So, autogenous vaccination is an effective, elegant, and profitable solution to control Streptococcus suis infection on animals. But autogenous vaccines are more, and because Streptococcus suis infection is a zoonosis, and because the control of this infection in swine required the use of massive quantities of antibiotics for years, Streptococcus suis autogenous vaccines are part of the One Health strategy. And as mentioned by the previous speakers, the preservation of efficient antibiotics and precisely the fight against antimicrobial resistance to a reasonable use of antibiotics and the prevention of zoonosis are two of the main targets of One Health concept. Regarding Streptococcus suis, you probably remember two dramatic outbreaks occurred on humans in China in 1998 and 2005, involving 240 people with a mortality rate over 20%. So those people were backyard farmers directly exposed to infection during the slaughtering of process of pigs that have died for unknown causes or been killed because they were ill. And during the second outbreak, almost 30% of farmers had the toxic shock syndrome and 60% of them died. Other illnesses reported were mainly meningitis and sepsis. Those outbreaks were caused by a bacteria belonging to the sequence type 7 of the serotype 2. Fortunately, this sequence type has never been isolated so far outside of China, meaning not in Europe. And this sequence type 7 is a single locus variant of the sequence type 1 of serotype 2 strains. This sequence type 1 being the most associated with disease in both pigs and humans in Europe, Asia, Africa, and South America, as you can see here. So this serotype 2 is for sure the most frequent one associated in Streptococcus suis infections in humans, but it is not the only one. Serotypes 14 and 4, 5, 16, 21, and 24 have also been reported. So what about Europe? In red here are the countries where Streptococcus suis infections on humans have been reported. Interestingly, the first description of Streptococcus suis infection on human in the world was published in 1968 regarding 2 cases which occurred in Denmark. But human cases are quite common, and we find many publications coming from more or less all the countries in Europe, and all those ones are recent ones. So this zoonosis is mostly found as a sporadic disease in individuals in contact with affected or infected pigs. This is an occupational disease involving farmers, veterinarians, and workers engaged in fresh pork processing. So the clinical signs, as I said before, are mainly nervous, with meningitis often leading to deafness, but also arthritis, septicemia, and even toxic shock syndrome, which can be fatal cases, are described. But the other issue associated with Streptococcus suis is, of course, antimicrobial resistance. This is becoming a major problem in Asia, and as Professor Fanning said, mainly from China, also for Streptococcus, with highly resistant strains which are frequently isolated from pigs, leading, for instance, to recommend to combine antibiotics to control the disease, as published by EU 2 years ago. And in China, another team showed 2 years ago also that Streptococcus suis isolates carrying resistant genes are able to transfer them to other isolates. And they use for that the ICE, the integrative conjugative element that Professor Fanning showed, presented before. So in Europe, A Dutch publication showed that most of the Streptococcus suis isolates are resistant to tetracycline. And in Germany, they are mainly resistant to tetracycline, erythromycin, and clindamycin, confirming the result got from human isolates of Streptococcus suis serotype 2 in Poland, which showed the same resistance profile. Another study in UK showed an increased levels of resistance with time for most of the antibiotic families. But the problem is elsewhere, as those antibiotics are not commonly used for the treatment of Streptococcus suis infections, which are quite easily controlled by the use of sulfonamides or amoxicillin. So the problem comes from the fact that antibiotics have been widely used to prevent disease in the past. And if we go, for instance, for 15 or 20 years ago, a program like this one was quite frequent, with, for instance, colistin in the feed at the weaning in most of the farm to prevent enteritis, followed by sulfonamides during 1 or 2 months in nursery to prevent Streptococcus suis outbreaks till the transfer to the fattening farms. So if those uses were efficient to prevent and control Streptococcus outbreaks, they had as a consequence the selection of bacteria naturally resistant to the antibiotic used, present in the digestive or respiratory tract of the animal treated, with a potential risk to infect humans or to transfer resistance to human bacteria. So this led to, as I mentioned before, to international or national plans to reduce the use of antibiotics. Here you have a page from the World Health Organization on the left and the French initiative called Eco-Antibio on the right. And Eco-Antibio is a 5-year plan. The first started in 2012, and we are now during the second one, which started in 2017. Such plans are implemented as presented before in most of the European countries. The WHO highlighted 3 alternative options to reduce the use of antibiotics, and we already, Professor Fanning said that before also, including improvement of hygiene, a better use of vaccination, and change in animal housing. So those plans are efficient. As for instance, the use of sulfonamides controlled Streptococcus suis infection was reduced by 82% in France between 2010 and 2016. And in fact, antibiotics have been replaced by the use of autogenous vaccines in farm where the disease was present. So practically, how to get such vaccine? So there are several key steps before and after the manufacturing of the vaccine, which make the vaccine successful. The 2 first steps regard the sampling of animals and then organs, so at the farm and by the practitioner. Then, at the diagnostic lab, the isolation of the pathogens representative of the disease. And finally, the characterization of isolates done either in diagnostic lab, either in specialized lab like done at Seva manufacturing plants, which allows the cell to select the most appropriate ones to include in the vaccine. And then the vaccine, of course, is manufactured and delivered to the farmer. But after vaccination, a permanent monitoring to update the vaccine if needed is also key. So I just want to detail quickly the different steps. First, at the farm, it's important to sample several sick animals from several outbreaks. And these animals, of course, are chosen because they express symptoms characteristic to the disease. So according to the clinical sign, we will sample animals with nervous disorder or locomotor problem, which are the most frequent symptoms we can find with this disease. The second step is to sample relevant organs and tissues characteristic of the disease. So in case of nervous symptoms, we will sample head or swabbing the brain. In case of locomotor problem, sampling the leg or arthritis swab. And in case of septicemia, heart blood, liver, spleen, or lymph nodes are on interest. The third step at the diagnostic lab, the recommendation is really to seed separately each organ of each piglet. And the golden rule, of course, is to isolate the strains in pure culture from lesions, and then to identify the Streptococcus suis colonies. The fourth step is a characterization of the strains, of the isolate. And the most important thing to do is the serotyping. This is compulsory, as there is no cross-protection between serotypes. The main or most interesting method to serotype, to identify the serotype, is a rapid agglutination test, which mimes the immune response. These tests are helpful only if the strain is well encapsulated, because in fact this method identifies the capsula. And some strains also autoagglutinate, leading to negative results. So in that case, we can also use another technique, which is a PCR, and which is useful, of course, for unencapsulated or autoagglutinating strains. But the weakness is that some serotypes cannot be differentiated. For instance, serotype 2 versus 1,2 and serotype 1 versus 14 cannot be differentiated. So the golden standard for the serotyping remains the coagglutination test, and eventually, in case of negative results, the PCR. We can also add other techniques, other methods to characterize the isolate, and to have more information also for the pathotype. So the pathotyping is a complementary information which can be useful, for instance, if you are not sure about the organ of isolation of the bacteria. Perhaps we will have questions. There is no sense for me to sample lung or, of course, tonsil. But if you have no information about the organ of origin of the isolation of bacteria, or if you isolate several strains belonging to the same serotype, but for instance with different profiles, this method is also very interesting to select the strains. And here you have two examples of the most frequent profiles found on invasive Streptococcus suis belonging to serotype 2 or serotype 9. So why to sample several rounds of animals, several outbreaks, and several animals, and several organs? The reason is simple. It's just because it's very frequent that several serotypes present in the same herd are able to cause the disease. Here you have a publication showing, so I do not know if you really see my cursor, but if you go in the table 2, you will see the column with different animals, pig A, pig B, pig C, and different farm. And we see that, for instance, for farm 1, 2 pigs samples with disease, with clinical signs, show different serotypes. The same for serotype 2, farm 2, with 3 different serotypes found, and so on. But also within a farm and in the same animal, we can find different serotypes. For instance, you see that from farm 5 to 14, with different isolates, different serotypes isolated from the same animal. And at the end, from farm 15 here to 21, you have different results with the same serotype, several isolates. For instance, for farm 15, 7 isolates belonging to the same serotype, but with different antibiotic profile. So in that case, which one to choose? And the pathotyping can be a response to this question. But this really highlights the fact that you really need to get several strains from several animals, from several outbreaks, in order to have an exhaustive view of the circulation of pathogen in herd. And on this slide, you have a practical example we experienced. So 4 farms, for instance, for farm C, 8 isolate, and these 8 isolates belong to 1, 2, 3, 4, 5 different serotypes. In farm J, with 12 isolates, we found 2 different serotypes. D, 15 isolate, 1, 2 serotype, and 2 which were not typable. So we were not able to, we do not know if they belong to the same serotype or not. That means in this farm, we have between 2 and 4 different serotypes. And in farm K, with 25 serotypes, we have between 5 and 9 different serotypes. Once again, because we do not know about the 5 not typable strains, if they belong to the same serotype or not. And of course, you cannot have this kind of result if you only sample one animal from one outbreak. And at the end, for me, the story is not finished when you have the vaccine administered in the farm. This is just the beginning of the story. You have to monitor the farm after starting the vaccination. Why? Because the pressure you have with the vaccination will allow you to reduce the excretion and to reduce clinical outbreaks due to the serotype or the serotypes which are in the vaccine. But at that time, because of the pressure we made to the dominant strains in the farm, this allows those which are dominated to emerge. And quite often we see new serotype. I say new because they were not isolated before or identified before, but new serotype emerging in the farm. So you have to update the vaccine in that case. So some practical examples just to finish this part. 3 examples, which in fact are quite representative of the most frequent strategy we can have and can see in the field, on the field. Farm A, for instance, isolated first 5 different strains belonging to the serotype 9. And the veterinarian decided, I do not want to comment that, but decided to include all these isolates belonging to the same serotype in the vaccine. And what happened quickly after the implementation of the vaccine, a new isolate, a new serotype was identified. So, of course, the veterinarian decided to add it in the vaccine. He removed some of the 5 serotype 9, which were in the vaccine, and added a new one. And a few months later, a new strain, which did not belong to any of the serotypes was isolated. And once again, this led to update the vaccine. To see the composition was really changing with time. In Farm B, the strategy was different. They took time to make several isolations. And the first isolate was from serotype 9, and 2 weeks later, the isolate serotype 8 and the not typable strain, and 1 week later, serotype 5, and then serotype 5 and serotype 9 again. So at that time, they decided to build the vaccine and to include in the vaccine one of each serotype, 5, 8, and 9, the 3 serotypes which were found, and the 2 isolates which did not belong to any of the serotype present at the lab to be identified. And the Farm C, another example, they were a kind of exhaustive analysis, sorry for the noise, and they isolate first 11 isolates belonging to the serotype 2, 6 to the serotype 4, and 3 which were not typable. And they decided to include in the vaccine 1 isolate from the serotype 2 and another one from the serotype 4. And a few months later, this is really the result of the pressure exerted by what we have in the vaccine. They isolated 1 strain from serotype 1 and 2 from serotype 9, which were not isolated previously. So they updated the vaccine, including these new strains in the vaccine. So it's really something which is moving, kind of dynamic, which is really needed to control the disease in quite frequent cases. So some results now. Last year, there were more than 600,000 souls vaccinated with several autogenous vaccines, including Streptococcus suis in Europe. And we got some reports from the field in different countries. And in fact, we see the same results everywhere. The post-weaning mortality, because most of the cases occur at the time, the post-weaning mortality are generally divided by 2 or 3. I am speaking about the total mortality occurring during the post-weaning. So the part of it is not, of course, due to Streptococcus suis. And with acute forms and high rates of mortality, like for example, in that farm in Spain, the gain is even higher. Antibiotic treatments, they are divided by 5 or 6 in this example in Netherlands and France, and by 2 in Spain and Germany. In fact, in those countries, the autogenous vaccines of those examples have been introduced more recently. So once again, I think that we need time to see the complete benefit of the vaccination. First of all, because you need 6 months to vaccinate all the sows of the herd and to have a quite high pressure. And as I showed you before, sometimes you have to update the vaccine. So we really need time, and you see progressively the increase and the gain, the complete gain of the vaccination. I would like to detail a practical implementation of the implementation of the vaccine in a French farm, which illustrates what we can expect as gain in terms of use of antibiotics. And I chose this farm. So this is a small farm, 220 sows, but it's quite representative of the size of the farm we have in France, which is around 250. And we collected the data from a period of 18 months before the vaccination. And this farm was interesting because the post-weaning mortality was under control, in fact. The Streptococcus suis disease was not really a problem. The problem was the use of antibiotics. There were some antibiotic treatments individually injected to animals by intramuscular route for 3 days, but mainly the use of antibiotics in drinking water. And in fact, you see here that more than 30% in average of pigs received during the nursery time an antibiotic in drinking water. So they isolated a strain belonging to serotype 4. There were only this serotype at that time isolated in the farm. And after a period of time, the same period of 18 months, we saw the result. Less mortality, even if the mortality was low before the vaccination, less individual treatment, but mainly no collective treatment needed to control the disease in the farm. But as there were some mortality, some cases again, they performed some analysis and isolated a new serotype, which was a serotype 7. So they added this serotype to the vaccine, and in fact, after a while, we see that there were no mortality involving Streptococcus suis. In that case, the mortality was mainly the disease was mainly associated to arthritis, and so there were not cases of arthritis on the animals, and very few treatment because only 3 piglets were treated individually during this period of 6 months. So even in that case where we have low mortality, we see that we are able to reduce the use of antibiotics, but you need time to get the results. So in conclusion, because I see the time is going, I would say that we have to remember, even if it's not a huge problem in Europe so far, because we are exempted of this sequence type which has been described in China, this is a zoonotic pathogen. And each year there are people dying in Europe because of this isolate. And those people are people working with pig. Antibiotics are no longer an option for the control of Streptococcus suis infection on swine. This control of the disease through the autogenous vaccination of sows is a relevant alternative to the use of antibiotics, but you need repeated sampling, accurate diagnosis, precise characterization of isolates, and permanent monitoring of the farm to succeed for the vaccination. So I would say that the vaccination is our business. This is our job to provide the best vaccines, but this best vaccine won't be successful if it's not produced with the right bacteria. And this is really your job as practitioner to explain to the farmer that you need to repeat sampling, diagnosis, and characterization or isolate before taking the decision to decide what to include in a vaccine. And I see by experience that when we are speaking about vaccine, of course, there is a cost of the vaccine, and the farmer is asking for the cost. Do not forget to add to this cost the cost of analysis, which is once again key for the success of the vaccination. And the cost of these sampling and diagnosis can reach 20% of the total cost or 20% of the cost of the vaccine itself. So it's significant, but it's key for the success. Sorry. Thank you.